Okay, quick introduction for those of you who don't know me. I'm Alisdair Meredith. I work at Bloomberg. My thing I've been playing with recently, I've now got a Twitter handle, Alisdair Meredith at Twitter, but well, generally I tweet just around about the ISO standard meetings to give a quick update as to what's been happening at that week. So my other sin is I like to attend ISO standard meetings, which is where this presentation is going to go. I'm going to suggest, highly speculatively, that there's no endorsement from either Bloomberg or the ISO process of this yet, but this is something I hope to be pushing over the next 12 months, the idea of a new allocator model for the new standard library. So we'll start with the simple question of what is an allocator? Let's be sure we at least know what we think I'm talking about. An allocator, I can look down here and see more clearly. It's a service that grants exclusive use of a region of memory to the clients that are going to need to use memory. That's my basic notion of what an allocator has to do. It's got a second side, that if you've got nice, well-behaved clients, they might want to tell the allocator when they're finished using that memory so it can reuse that region now for somewhere else. So that's my basic model of what an allocator is and does. Why do we want allocators? And the fundamental question here is the new operator not good enough? Can we get by just making the new operator better? And don't get me wrong, we all want better new operators. That's not a reason to stop investing in research and making this better. So the fundamental reason, I believe, for allocators is performance. Shortly followed by performance, and then more performance. This, from talking to folks who've actually tried working in this domain, seems to be the key driving factor. It's actually not what I tend to use them for so much at work. I tend to use my fourth option here, instrumentation. I find being able to enrich the information you have with an allocator, query its usage, has been very beneficial for us. But I'm an outlier. Performance is the main reason this whole talk was created in the first place. And final note on things people sometimes want to use allocators for is special memory access. I've got a slide about that just coming up shortly. So when it comes to performance, I'm not going to say too much about that now, because hopefully tomorrow at 2 o'clock in room 403, John Lakos is giving a talk all about the measurements we've done, benchmarking, to try to determine the benefits we can get from different allocator strategies, whether they're how useful they are, whether we can measure it, and we think we have some good results to show there. But my quick takeaway from that, with sifting through reams and reams of data, is when we benchmark the performance of the allocator just doing allocation type behavior, where we have a well-chosen allocator, we can typically get a 3 to 5 factor increase on throughput on the allocator. And if you start finding out the extreme outliers, we can certainly get orders of magnitude. The interesting thing that came out of this research, though, was that, again, if you were in the previous talk, you'll have heard some about this, is that better memory locality that you get from a well-chosen allocator buys you significantly more performance after the allocation. So this is the real performance that we're trying to achieve. By allocating memory locally, so it's friendly for cache lines in future access and use throughout the system, you're going to get generally a faster program, certainly on your hot path and the performance-intensive parts of your code. And this is where the notion of memory pools comes in, where different structures will allocate from different pools, so each pool will keep the data local for a specific container, graph, overwhelming data structure, whatever you've got. Having a separate pool for each data structure, at least the ones you care about for your performance-critical code, can make a substantial improvement on the runtime of your application. Another observation, when you've got long-running processes, memory fragmentation over the whole address space can become a concern if you're trying to run this process for months, weeks, years, whatever. And if you can allocate memory locally off the current stack frame if you've got small allocations. This can substantially, again, reduce the eventual drag on the system as a whole. So that's another place where we can gain performance and indeed gain reliability over the long-running evolution of long-running server processes. Key issue, I hate to harp on this, but again, I just sat in a talk where we spent an awful lot of time talking about the benefits of getting good cache locality, so I feel redundant having just a line or two about it here. But the more you can take advantage of well-aligned memory with the right pages to shoot through your L1, L2 caches, the more performance you're going to get out of your process. And to do that, you really want to be able to give the allocation system some hint to say, this memory I want to keep collected over here, and this memory over here, so they're in distinct regions. And you can't get that from the simple hints to operator new. There's two main strategies we've been using, effectively referencing on those previous slides, and John will be talking about tomorrow. One would try and allocate off the thread stack, but that's as local as memory can get because that's where your instruction processes, everything is going through. It's where all your local data is. And you're not having to do additional management. The stack just takes care of itself, essentially, with the compiler. The other thing that is very beneficial is, as I said, managing pools. I should probably have an extra slide in here about the actual allocators we use. The notion of our stack allocation is we're going to provide a pre-sized buffer on the stack, and at some point you might exceed that buffer, in which case we'll go and grab a bit more from dynamic memory. But we've got a buffer that we treat as one long region of memory that is very cheap to allocate from. All we're going to do is move the stack pointer through it, and we never give that memory back. This is very good for certain kinds of data structures, and this is, as I say, the stack-based notion of some code works very well. The problem is if you start churning memory, you're handing it back to the allocator and reusing it, that quickly will exhaust what it can do. So the other notion is you have a pool that will, manage a sub-allocations in there, so that when you hand the memory back to the pool and you request a similar amount, so I'm inserting and erasing frequently from a single container, that memory gets reused much more frequently. And then again, this is where you want separate pools for the separate data structures. And you can layer one of these on top of the other, which then means my problem I was saying with the very efficient stack allocation, where we just move a stack pointer all the way through and we never reclaim the memory. If you put a pool allocation in front of that, that will mitigate the fact that you've now got something that is managing that bit of memory you've grabbed. My bad, I should put an extra slide or two in there. But the fundamental question is, why do we want allocators? And is the new operator not good enough? And the observation is, most of the time, the new operator actually is pretty good. It's good enough. But when you get to the essential critical parts of your system, the parts where performance really matters, and you, as the application developer, have much more information about the context and the way you're using the memory, you can make a real difference here. And when you want to plug something in, operator new doesn't give you the knobs and whistles that you need in order to control that facility. So that's where we want to use allocators. As I said, an extra facility we have once you have the ability to plug in allocators is you can do extra utilitarian things with them. You can have them to support debugging. You can log your memory allocations, which is on the way towards being a profiling system. And the key one I use them is for test drivers, so I can confirm that when I'm testing my code in unit tests, that the memory allocation behavior is actually allocating the way I expect, and I don't have unexpected leaks, double freeze. I'm suddenly allocating more memory than I expected. Why did that happen? Having an allocator that's instrumented for test drivers is very helpful in maintaining the quality of your code and getting the behavior you believe you're getting. The final corner, we have the notion of special memory. Shared memory is probably a common example of this, where We might have some memory we're trying to share between processes, so we need to access it in a special way. Some hardware systems have memory with special access routines that you have to access in different ways, NUMA systems maybe. I'm not sure if getting access to the VRAM on video cards these days. This isn't my area of expertise, but I'm assured that these systems certainly exist, and hopefully some of you folks out here have more experience with them than I do. But that's another aspect that people look to for allocators. So with that, sorry, dying of thirst here. It's been a long day already. I'm going to take a quick look at the brief history of allocators in the C++ standard. So let's go back to C++ 98. Why did we add allocators to the original standard? And the answer was simple. It was near and far pointers, back to those funny accesses again. And that was essentially the only reason we had to add allocators to C++ 98. But why did we do it in the mechanism we did? It was a speculative notion that if we have to customize it for this now, we're going to want to customize it for more things in the future. So let's put in the facility with a customization point that we can then experiment with and start doing more interesting, useful things with. So the basic notion, I'm probably teaching my grandmother to suck eggs here. Who's actually played around with allocators in the C++ standard containers and things before? So I'm seeing about half the audience. So basic model is if you have a standard container, the template parameters have at the end the idea that you can say this container works with a different kind of allocator than standard allocator that I'm going to supply. The model that we came up with is that allocators are allocating memory for objects. So the allocator that you plug into your container is also going to be a template that's parameterized on the kind of object that it's going to allocate for. So for a vector that allocates int, and a vector of int and a vector of float, they're going to have two different allocators, because one knows how to allocate for ints and one knows how to allocate for floats. Even if they happen to be the same size, returning exactly the same amount of memory, they're different allocator types, doing different things. Which means that each allocator and each container with these different allocators being plugged into them now is a new type in your type vocabulary. And vocabulary is an important issue when it comes to API design. Because if I want to have easy interoperation of my code across the system, I need to be passing common, well-understood types. And if every time I want to do something subtly different with my allocation strategy, I create a new type, is that new type a reasonable type to have in the interface? Do I need to do translation now between my types, which might mean copying the data around again? So just for the sake of vocabulary, having allocators as template parameters on our containers could be a bit of a problem. But it's also brought us a bunch of other advantages as well. So let's not throw the baby out with the bathwater straight away. We'll do that in about another 20 slides. The other thing we got with C++ 98 was, because the whole notion of allocator was a bit speculative and new, we gave the implementations freedom to ignore a couple of properties that you would get from plugging in an allocator when you create your objects. And the first thing we did in C++ 11 is we started trying to tackle the notion of how well can allocators be used in practice, was remove those Weasel Words. So the notion that back in C++ 98, you might have heard that allocators are useless because you can't do anything with them, certainly seems to be true in C++ 11, because little bits of wording that told vendors, I can make simplifying assumptions that ignore the vast majority of what your allocator is going to do, those have gone away. And in order to make life a little easier for the container vendors, the people implementing their data structures, we provided the Allocator Traits facility, which does all the clever work to try to figure out sensible defaults and routine behavior if you don't have an allocator that provides everything, so that allocator developers focus on just what their allocator does. Container folks say, I'm going to access the services of the allocator now through this allocator traits rather than going directly to the allocator. And we threw in an extra allocator in addition to standard allocator, standard scoped allocator adapter, which basically is a neat package for supporting nesting of different allocators at different levels of your system, so that if I have if I just have one allocator in my scope allocator, it would mean that my elements will use the same as the container itself. And I'm doing something funny with my microphone. I'm jumping in and out here. So just a quick recap on the Weasel Words that we struck going way back to C++98. There was an assumption that all instances of a given allocator object would always be the same. They were always interoperable. And the translation there is that your allocator objects prior to C++11 could not reliably have state. And if your allocator object doesn't have state, it's really hard to do a lot of the interesting things we want to do to make allocation more useful and powerful. And in particular, you're not allowed to have a pointer to another mechanism that's looking after a lot of that allocation for you. The other part of the Weasel Words was we've got a bunch of type defs that you have in a allocator that say, this is the kind of pointer I use, this is the, how you measure the size of allocations and so forth. And the implementation was allowed to simply assume that these are always raw pointers. And that means that you can't have allocators returning fancy pointers, C++ smart pointer type things that allow you to encode those special rules for allocating out of special memory regions and making sure that I've got pointers that do all the appropriate wrapping to get into that special memory region that I'm trying to do clever things with. So by striking those bits of Weasel Words, C++11 allocators now can support the models to do all the things that we were talking about and want to do. Quick walkthrough of what Allocator Traits looks like. You have, it's a class template parameterized that says on the allocator that you supply to it, and your allocator has to have a nested value type because this is still modeled on the C++98 model. Allocators allocate for objects. So the allocator that I plug into Allocator Traits is going to be a class template, and it's going to say, I know how to allocate for this kind of object. And then we have a bunch of other type defs that are really useful when you're dealing with allocations to say, what kind of pointer or constant pointer to the allocated object I'm going to get. Pointers to void, just for general access into that memory buffer. And if the allocator provides these, Allocator Traits picks them up, and otherwise it will compute a good default for you so that people don't have to worry about minutiae for their allocator that they're not dealing with. Likewise, we need to be able to rebind, because allocators have to be class templates, we can rebind from, I've got an allocator for int, and then I want to store it in a list, so I need to have a node that holds an int. So I need to allocate something different than the allocator the user gave me. I can rebind and have an allocator for the kind of thing I want to allocate for now. From the same family, all through the allocator traits. And finally, things got interesting where, when you go to actually perform your allocation now, you're going to use these static member functions of the allocator traits template rather than access the allocator directly itself. So you'll see this is a utility class where all the member functions are static. There's no intention that you'll ever instantiate an object or create an object of this type. And the first argument to every one of these functions, you will notice, is the allocator that you're trying to use. But this allows the traits class to synthesize the operations that the allocator might be lacking. And the interesting thing I'll just call out in passing, as I always do, the allocate and deallocate functions work in whatever kind of pointer type your allocator has, whereas the construct and destroy methods, which are customization points to say, now I'm constructing something that might want to know about the allocator I used, those actually just traffic in the address of the object I'm creating. And for convenience, they're templates, so I don't need to keep rebinding these as I'm trying to construct 3 or 4 different things with the same allocator. So that's just a little gotcha to be aware of that doesn't catch people out until they start using smart pointers for the first time, and then suddenly discover these APIs are subtly different than they thought they were. And then we come to the joys of allocator propagation, which I've got a few slides coming up shortly, so I'll jump over those. But those are another aspect that you'll find in the traits that turn out to have a big impact on how we use these things. So progress in C++98, we now support a wide variety of allocator models, because, you'll spot we've got 4 different traits here for propagation. Most of those are Boolean, so that's a binary choice. So that's at least 16 different allocator models, depending on how we plug things in there, regardless of what we're doing with those, because these kinds of allocators will all behave very differently, as we'll see. So we've actually supported a much more than just a new allocator model. We've supported a facility that supports, I'll not say every imaginable allocator, more than I care to think about. But the interoperability of vocabulary types remains an issue because the allocator is still tied to the type of object it's allocating. The data structures that consume these allocators are still templated on the allocator type that I'm plugging into the container, the data structure, because we couldn't change that. This is just an enhancement of the existing standard library. And if we make a change of this model, we're instantly giving up compatibility with that library. And we can't do that while maintaining that same library. Skipping over C++ 14, I don't remember much happening with allocators in 14, apart from maybe some cleanup of the wording. How did we improve allocators in 17, just to bring us up to date with where we are today? Sorry spending so long on laboring the history, but it's good to know what we're trying to change before we start, and what problems we have before we start trying to solve them. We've got a new trait is always equal to say that these two allocators, any two objects of this allocator type are always interoperable. So I don't need to actually take a look at the state of those allocators to see can they interoperate, one allocate and one deallocate the same region of memory. And this is very useful when it comes to providing no exception specifications. Because if I know that the two allocations are always the same, I can start making better no-throwing assumptions about move semantics and a few other places. So this new trait ends up appearing in quite a few exception specifications related to swaps and moves throughout the standard library. We also added another facility called polymorphic memory resources, which again will be, actually I don't think this is too much of John's talk tomorrow. This is the inspiration for John's talk and this talk. But the notion of a polymorphic memory resource is we provide a new model for allocators that rather than allocating objects, just allocate memory. We then wrap that up in a C++ 98 style allocator that knows how to allocate objects out using this memory resource. But the notion now is we have memory resources that are just about managing memory, and we wrap them in a C++ 98 style allocator. And in addition to that, we have PMR containers, which is PMR, short for polymorphic memory resource, just trips off the tongue. It's a namespace within std, and then within there we have an alias template for every standard container that just says rather than using standard allocator, I'll use the allocator that wraps the PMR resources instead. Because we don't need to do any other work. It's just we're plugging in a different allocator policy. All the work for doing allocations correctly is already implemented in the standard containers. So this is not a whole new set of separately implemented containers doing lots of different interesting things. It's just an alias template that says, yeah, I'm plugging in a different allocator. So the PMR containers have one fewer template parameters because the allocator is already picked for you. And the final tweak we did for C++ 17, not that relevant for this talk, but I'm trying to be complete, is we now require that when you use those fancy pointers for special memory regions, the pointers they return have to be contiguous iterators. We used to have the notion that perhaps somehow a secure system, you might want to actually have a security cookie or something between each allocation. And therefore, when you implement the pointer semantics, your operator ++ would have to know how to skip over those little cookies. But people doing address arithmetic on the allocated objects are now going to get the wrong answers. You have to do everything through the pointer type. By requiring those to be those fancy pointers to always be a contiguous iterator, you can now do pointer arithmetic safely with the objects in your containers, where you've got contiguous guarantees. So how does the polymorphic memory resource system work? Time tick. We have a basic abstract base class, standard PMR memory resource, that provides a basic interface for allocating and deallocating memory. I've got that on the slide to come. Clients are going to store pointers to that base class. And we're going to use them with traditional vtable style C++ programming. We've got a pointer to this thing is the service that's providing me memory. And now clients can plug in their implementation of that interface. And at different times, I can plug in different allocators without changing the type of the object I'm dealing with. I'm just picking the strategy at runtime now. And going back to when I was talking about those propagation traits, the key issue is that the resource pointer never propagates. And for folks who haven't dealt with stateful allocators, I'm going to spend a couple of slides now talking about why the propagation property matters and can be surprising to people. The final issue that we have with the PMR model is that when I have a container using polymorphic memory resources, so I've got a vector. If I have a vector of strings, I want to guarantee that the strings are all using the same allocator as the vector. We don't support the idea that I've now got a vector of strings and each string is going to have a different allocator. The whole notion of being able to rely on memory being in a pool is that all the elements in the container have to have their memory coming out of that same pool. So the work is, the allocator is going to say when I construct elements in my container, this is what the construct method for is therefore in allocator traits, I'm going to make sure I propagate is a word I want to use, but it means something different in the standard. I'm going to pass that allocator down to the element when I construct it. So this is the basic memory resource interface, which looks a little small on this slide, I'm afraid. Basically, you see it's got a virtual destructor. It's got public member functions that are not virtual, allocate and deallocate. And they take a number of bytes that you want to allocate and an alignment. And the alignment will default to max align if you don't supply it. And then we have protected pure virtual functions that are again, the do allocate and do deallocate that the memory resource is going to implement. And the idea here is with the public member function, I can have a defaulted argument, so I've effectively got two functions for the price of one. But when I'm implementing an allocator, I don't want to be implementing two different virtual functions. So the function we call always takes, that we dispatch to internally, will always take the alignment, even if I choose to ignore it. So these methods are virtual. These are the allocate and deallocate are the key member functions that clients of the allocator are going to use. The do allocate, do deallocate, using this idiom, as I said, so we can not worry about funkiness with default arguments on virtual function calls are what the memory resource implementers are going to implement. And our choice of vocabulary types for how do I refer to memory is a void star. We have the option, it could be void star, it could have been char star. It came into 17. It could even have been byte star if byte hadn't landed so late. But void star, on balance, turned out to be the right answer as we're developing this proposal. I'm going to skip the do is equal part for now. So idiom and usage of PMR. The notion of my memory resource is it's going to be an object like any other that it owns and manages a region of memory. And I'm going to create it locally in my function on the stack, just like any other variable. And now, once I've got that object, the lifetime of objects below it can happily use that memory, because as long as they're destroyed by the usual rules of the C++ language before the memory resource object itself is destroyed, I know I'm not going to have any funny pointers and references to memory I don't own. So the basic model is, in your function, you're going to create on the stack your memory resource object, which that slide I was missing earlier about the on the stack or in the managed pool, those are the kinds of things we're talking about here. And then I will allocate out of those when I will pass those memory resources to the containers that I want to be managing. I tried going through this too quickly. I don't have enough informative slides, unfortunately. First time I'm giving this talk, and I'm realizing I'm afraid in front of you what I'm missing. We've also got three other notions of special kinds of allocators, or terms we use for the allocators, or these memory resources. I keep pulling on the term allocator because that's what we've been calling it in Bloomberg for the last decade or so. overload. The default allocator is we have a system-wide default to say, if I don't request a specific allocator for this object, use the same default that the rest of the system is going to use. And by default, that's going to be operator new, but we have the ability to customize that globally across the system as a whole. The notion of the object allocator matters in the context of I now have an object that's managing memory. I'm owning and managing a data structure. The object allocator is the allocator I'm going to use to allocate nodes, allocate buffers, things that are going to persist beyond a member function call. And the idiom is, if someone invokes a member function, and I have to ask the question, which allocator should I use? I've got the default allocator, or I've got the object allocator, because I know which allocator my object's using. And I'm just creating a string object that's going to be used within this function and go away. Always use the default allocator for those temporary objects allocations that do not exceed the function call, because those are not part of the persistent storage of your container, and they're not expected to be part of that memory resource. When people compute their expected size of that container, the amount of memory it's going to consume, they're not looking for these funny transient allocations that occur within member functions. Whereas if I'm going to allocate something that's part of that data structure that's going to persist beyond the function call, clearly that should come out of or be allocated using the object allocator. And then you get the fun things like, okay, I'm going to do my work, I'm going to create this object on the stack, but then I'm going to transfer it into the data structure when I'm done. In that case, the intent is that the object is for a persistent allocation, so you use the object allocator, even if we end up throwing and that memory then gets reclaimed. And final notion is we have something we call the global allocator. This is not part of the standard PMR process, but the notion is still good. And if I have an object of static storage duration, or thread local storage duration, its destructor might happen after main has concluded. And if I've installed a system-wide default allocator, that's probably been installed somewhere in main. So I want to have allocations for global persistence, static storage duration objects that might persist beyond the registration of the default allocator. Each should then have its own local allocator just for that object, or we have a global system that, again, runs for the duration of the process. The other key thing, though, that comes out of the PMR system is we no longer have support for fancy pointers. If I jump back, where's our virtual functions? We've got our virtual functions here. And they return void star. And they work with void stars. And because they're a virtual function, that's the signature I'm bound to. I cannot plug in a different fancy pointer and try and override this member function, because it's the wrong signature. So as part of choosing this ability to plug in our allocators at runtime rather than compile time, we give up the flexibility of the fancy pointer. That's our trade-off. To an extent, we do get, for instance, we still want to work with shared memory at Bloomberg, and we do this by simply ensuring that memory segments always load into the same address in the address space of all the different running processes. It's a bit, there's tricks and means that you can do to make this work. So you can ameliorate some of this. But for instance, I think Herb Sutter had an interesting talk about using fancy pointers for garbage collection last year, and that might run into an issue here. So this is still something that I don't have the silver bullet that solves all the problems of all the array of allocator models that I was mentioning we could build. But it's a very specific solution for trying to ensure we can have the maximum flexibility that we can support at runtime. The key thing is it solves a vocabulary problem. So these things are very good for the kinds of objects you want to be passing through APIs. You don't have an interoperability problem when different objects are using different allocators. I say we've given up the support for the fancy pointers. There's an implied cost here, though, that every object now that manages memory is storing an extra pointer to the allocator. This is Not a cost that was paid with the traditional standard allocator that just dropped everything down to standard new, or any allocator model where the allocator type itself was just an empty type. John will talk about this somewhat tomorrow. And again, the other cost is now that our memory allocations are a dynamic dispatch rather than a straight function call. John will have measurements tomorrow that show typically these costs turn out to be negligible. But there are concerns that some people, when they're down measuring at the nanosecond level, might have some of these concerns. The goal is that we gain enough elsewhere that it swamps any potential cost of the dynamic dispatch when you're not using the facility deliberately. As I say, Bloomberg, we've been using this facility for over a decade now. Not explicitly the PMR that's in the standard, but essentially the progenitor that became that. It's mostly the same without the support for alignment. That's a little bit more subtle. Our experience is that the PMR allocators have been a big win on performance, especially in performance-critical code where people are invested in making the effort to use the facility. I found, there's certainly other folks around the company, but especially me, have found the instrumentation helpful in getting our test drivers much more reliable. It's fantastic, the ability to be able to instrument and profile and do interesting things with the instrumentation. But performance is the real key everyone's using this for. And despite all these great things that we're saying allocators are wonderful, the user still bridle at the complexity that comes with trying to plug allocators into the C++98 model. Just seeing where I'm on time. I've got 20 minutes to go. Am I? And what's my slide number? Yeah, this will be behind. So the first time I'm giving these, I'm never very good at pacing myself and then race through all the interesting stuff at the end. So, complexity of C++17 allocators is a problem. Why does complexity matter? Complex facilities frequently are simply not used. They're intimidating. They're more work than people want to run into. Good example, C++98, we had a very powerful IO streams facility. And I know very few people that do anything other than use the straight IO streams that come out of the ISO standard. In fact, they often don't use them as templates. They just use the type defs of standard stream and overload a few insertion operators, and that's it. Again, the slow adoption of use of allocators from the standard library. The facility's been there for a long time. And it's only in the last 4 or 5 years we're starting to see users experimenting and using this facility a bit more. Certainly, Allocator Traits in C++11 made it a lot more interesting to experiment in this space. But even if we've got this facility that we're not using that complexity, we're still paying the price for it. It's an intimidating thing to learn. Implementers have to pay the cost of implementing these things. And a complex facility, it's more expensive to compile. Are you paying a runtime cost? Most of that complexity is there actually to eliminate runtime costs. But the innate complexity is itself a problem. One of the biggest concerns that I had hit, or perceived notions of complexity when we're dealing with the 98 C++11 allocators, get the right standard version, is the notion of allocator propagation. Because this is where the PMR model and the preceding model in the standard where you had a stateless allocator start showing interesting divergences in people's intuition. So certainly you're going to provide an allocator at the time you construct an object. I've now said this object is allocating using this strategy. And I now assign another, so I've got a string, I assign another string to it. And the string I assign has a different allocator in it. Do I replace the allocator my string said it was using and says this is how I manage my memory? Because I'm now being assigned the state of this other string that says, no, this is how I allocate memory. Which allocator should be used for the purpose of the assignment? And this is where we have those multiple propagation traits in this C++11 allocator traits template saying, well, different people have come up with different answers. They want to do different things. And in fact, we gave them multiple dimensions to do different things. We've now got this dizzying complexity of the ways that we can do these things. So I was looking for a point I thought I got on that slide. I need to walk through my slides more frequently before I give them, I think. Not getting a bold, confident portrayal today, I'm afraid. So in terms of the PMR model, and the model I'm going to propose, you do not rebind allocators on assignment, on swap, on any other operation. The notion is, when I construct an object, I'm going to say, I know how this object, within its lifetime, expects to manage memory. So I'm giving it an allocator, it's fixed for life. And the reason this matters is because I'm also going to make the assumption that all the elements that I allocate are going to use this same allocator. So if I have a vector of strings, I expect all my strings to be using the same pool that I was given, if that's what the allocator does. Everything's using the same allocator. Somebody assigns to one of those strings as my data member, and the allocator swaps out underneath me. I've broken an invariant that I assumed when I designed the whole data structure. So that's one fundamental reason why we do not want allocators to be reassigned. Pablo.
I'll just point out that my entire talk on Friday is about some of the issues you're talking about here. So if that helps you to move on to the things you actually want to propose.
Pablo points out he's going to go into more detail about the problems I'm talking about on Friday, and specifically about the propagation. Yeah. Yeah. So, and lots to do with the complexity that PMR, you might hit with implementing it, and certainly it helps solve. Very quick, John.
Just want you to mention that PMR simplifies, not complicates, the use of the allocator model. C++11 is very different.
John wants to point out that the use of PMR simplifies rather than complicates the use of allocators, and yes, that's the point I want to get to. But when people hit allocator propagation for the first time, it's a roadblock and it stumbles people. Because when you have a stateless allocator, like standard allocator, does it propagate or not? It doesn't matter, because you're going to get the same execution regardless, because there's no state in the allocator. And there's some consequences follow from allocators not propagating that I'll defer to Pablo's talk on Friday. But as I say, the traits give us control over the propagation strategies, and the default in the C++11 allocator traits is at least that allocators don't propagate, which is the default we're going to want for the PMRs. The other reason that propagation matters is when I imbue my container with an allocator, remember the model I gave you at the start, I'm going to have a memory resource, and then I'm going to have a container using that resource, and the elements of that container use that resource. The reason I know that I'm not going to have to worry about memory being used outside the lifetime of that resource is we've got the guarantee that that whole data structure lives in that resource. If someone starts being able to move that memory in, those elements in and out of that memory by changing the allocators, it becomes very hard to reason about the lifetime of the allocated memory, of the managed memory that's managed by the resource. So we really don't want people swapping out allocators once objects have been created underneath us. So the big problem we got with the complexity of the propagation model that's in 11 is it's too versatile, and it leads to strange things. What does it mean if an allocator propagates on move assignment but not swap, or vice versa? And writing test drivers for these things is horrible. Implementing the thing that passes the test driver is worse. The syntactic overhead of dealing with a lot of this is relatively high. If you're now using C++ 11 allocators, using the allocator traits facility, all your management of memory now has to go through allocator traits. And we've now got this very expert-friendly facility. We want to move away from expert-friendly. That's what I'm trying to get to. Because we don't want people to worry about allocators unless they're using them. You end up with a default that we've got a constructor if I don't give you an allocator that just says use the system default, and then one that does use an allocator that I can supply. So we're potentially doubling the number of our constructors now, because every constructor has to have an allocator-aware version, which we might be able to handle with use of a default argument. But if we do that, we now need to have a default argument at the end of every constructor, so that if I've got a constructor that has 4 or 5 default arguments, such as in unordered map, I now need variants with an allocator at the end of each list, which produce a lot of constructor spam, as we saw in unordered map, for example. In C++11, it has 8 constructors. In C++17, it has 15 constructors, all to solve the same problem. It was just dealing with those default arguments, so we've now got a few constructors that delegate to other constructors. And part of the way we solve this is we just want a different way of passing allocators. So we've now got a convention where we pass allocator argt and the allocator as the first two arguments. That's great for all new code going forward. I can have as many default arguments after this as I like. But unfortunately, we're baked into an interface in the standard where already we had allocator passing as the last, not this encoded first argument. So now we've got two ways of passing allocators that code has to be aware of, which is not great. Then we end up with generic wrapper types like pair and tuple, because they don't know the element you're constructing. I might need to pass allocators through to the elements of the pair, even though the pair itself doesn't allocate. So now we have allocator support in things like pair and tuple, because we have to be able to pass the allocators down through the library. Even that's not good enough, because unfortunately we hit things. Sorry, next slide. I'm going to skip that one. We hit other problem cases like standard array and other aggregates, where because they don't have constructors, I don't have the ability to give them an allocator even if I want to. The same is true for a native array, so an array of strings. And that problem goes down a level. So if I've got a vector of array of strings, I can pass my vector its allocator. That can't pass down to the array, so the array can't pass it down to the strings in the vector. So there's these holes that we really want to try to fill. And again, there was a problem with type erasing allocators in type erasing objects like function and any. I've run too slow, I'm going to run past. I'm really running out of time. I've not got to my talk yet, I've got 10 minutes to go. So let's get to my proposal. Sorry, I planned to be here 10 minutes ago. It was heavy on the introduction, so you knew the problem we were trying to solve, but I've got half the time I wanted to solve it. Again, this is my personal vision for std2. The way we solve a lot of this complexity problem is we agree on a single allocator model. So we no longer have allocator traits to try to solve all of this mess. We have a single, well-defined way to do this, and that promotes all our vocabulary for the interoperation of APIs. The anti of going with a single model, of course, is you're going to have less customizability and flexibility. So we pick the most flexible model we know, which is the PMR system. And the key thing is we keep allocators out of the type system, which greatly simplifies things and gives us the vocabulary notion. We want to keep allocator spam out of the interface. None of those constructors everywhere all taking allocators. We need to find a different way to get the allocators into the objects. We're going to bake in the notion that if I've got a data structure, the whole data structure will always use the same allocator. That's going to be built into this model. It's a built-in assumption. If a type does manage memory, it will always do so using this allocator system. So I know it's plugging it in at one end of the system, it will be used all the way through. And we're going to introduce the notion of allocator aware types that are known in a special way to the type system. So in the proposal I'm going to come up with, a type is explicitly allocator aware if we mark it in a way that says this type is allocator aware. And that's going to mean something special that we're going to talk about quickly. And a type is implicitly allocator aware if it derives from an allocator aware class, kind of like, I've got a vtable, if my base class is polymorphic, I'm polymorphic. But unlike regular virtual functions, also if I have a data member that's allocator aware, I'm going to pick up this funny allocator aware tag. So it's viral on members as well as bases. Why is it important that we have this property for members as well as bases? Well, for generic code, I don't want to have to conditionally derive from something if I tried implementing it through some kind of base class type mechanism. But fundamentally, for aggregates, we know we can't solve this problem if I have to introduce a facility that means my type's no longer an aggregate. I can't solve native arrays at all this way. So the notion is we're going to store this PMR pointer somewhere, somehow, and it's going to implicitly find its way through the system. So an allocator aware class will use this PMR allocator I supply, or some variation of PMR, whatever works for the model, to manage the memory. There'll be a consistent API across the system that says, if I'm given an object, I can query it and say, what allocator do you have? Or do you use allocators at all? And this allocator is assumed never to change during the lifetime of the object, the non-propagation trait. Querying matters because when I come to things like move and swap, knowing if I've got the same allocator at both sides turns out to be a big deal. And there's a few other things that I want to jump through. The notion of implementing allocator awareness. Got your slides slightly out of order. I thought I was going through them in. Jumping into implementation details before I've quite described everything I wanted to get. But we're going to stash away an allocator pointer or a memory resource pointer, kind of like a vtable. And it's going to be consistent all the way through our hierarchy as we start allocating, creating new objects, as I pass down to my members. My members will all have, again, pick up that same allocator. We're going to customize this API to say, implicitly the system knows how to store this pointer away, but if I'm implementing something like standard optional, I know that when the optional is holding an object, that object has an allocator, so I don't need to store a copy. But when the optional object is empty, I need to retain a copy of that pointer, but I know that if the object I was storing was allocator aware, it's at least as big as that pointer, so I can reuse that same region of storage. So I'm going to want to be able to take control of this mechanism and say where that pointer is stored, and it might even be changing where it's stored at runtime and where I find it for some of these use cases. So that's the ability we need to have within the facility itself. And if allocator awareness is implicit, well, that means that something, either my bases or my members, already has allocator awareness built in. So I'm not going to store an extra copy of that pointer. The implicit system knows. I just keep going down the chain until I find that pointer. So we can at least push all the allocator pointers out to the leaves of the data structure. So we don't get to lose all the duplicate pointers, but we can implicitly reduce some portion of them. So the notion of implicit awareness is if I have an allocator aware type, or if I have a type that's built out of allocator aware types, it itself will always be allocator aware. Yeah. The key issue was allocator injection, which unfortunately I've got a very small point size on this. The idea is when I now construct my allocator aware object, I want to be able to supply its allocator not as a parameter to the constructor, but I'm going to have a separate mechanism to say, as I run the constructor, here's the allocator to use. So for allocator-aware types, all constructors have a hidden additional allocator argument that the system just knows how to pass down through. So at this point, I have taken allocator out of all my constructors. They no longer appear in the interface of the code that implements these things. The system knows how to pass them down through. So I have no code to write to pass the allocator in my member initializer list through the rest of the system. So ultimately, all the code and complexity perceived in the system goes away, because the syntax is, there is no syntax, other than those few places where I actually have to directly interact with the allocator itself. So this is kind of my mental model. I'm not saying this is what the facility should look like, but this is the notion of how we might be able to use this. So we're in C++20, we already have concepts, great. I've got template movable type class vector that says, I inject allocators here. So I'm explicitly stating in this case that vector is allocator aware. Then we'll have an alias called not aware for tuple of int. Well, tuple doesn't need allocators. Int is certainly not allocator aware, so a tuple of int is not allocator aware. Whereas a tuple of int and vector of int, vector is now allocator aware. So I've associated with the tuple tuple with a vector in it that this type will be allocator aware, and now its constructors have this extra allocator pointer hidden behind the system. For the implementer of vector, of tuple, it's just going to happen by magic, they don't have to interact with this because this implicitly falls out of the system. So I now have my local allocator from stack, saying basically I'm going to try and allocate off some stack resources. Vector of int, data 1, 2, 3. I've not given it an allocator, it just uses the default allocator, which will typically be operator new. We're going to have another syntax to say, when I construct this object, I'm again using the attribute syntax, hopefully we can find something neater, but it seems to work. I can inject from stack. And from stack is an allocator, so we've said we inject at the allocator facility. So it says, okay, whenever I call a constructor, I'm now passing in the from stack allocator. I've set that's what it will be. So the implicit extra argument to these constructors now knows to pick up the from stack pointer and pass it down through its member initialized list to all its bases and members all the way. And obviously we want to be able to do allocations with new and delete. So when I do a new, you can see the bottom example. New inject from stack, I put it on the new call. So that performs the allocation using that memory resource and passes that memory resource through the implicit system I was talking about as the additional constructor argument all the way down through the chain. So a lot of this implicit argument passing means the complexity is all hidden from the users. There really is not much more to it syntactically when even implementing these containers than this. So your containers use the allocators internally. So when your container has to do an allocation, it's going to have to go to retrieve this, perform the allocation. But the vast majority of your types, especially in modern C++, we learn not to write new and delete because these things are all wrapped by objects that are already managing that memory for us. And that gets pushed way down the system. Most of it comes out the standard library. Trying to figure out which of these to jump through quickly. Where am I in my slide numbers? I think I'm about over, actually. So, sorry, paced myself badly today. We're done.